Hello everyone, I'm Irene and welcome back to our series on OECA. In this episode, I'm going to talk about shell basics and show how to write shell scripts through practical examples. The shell acts as a bridge between users and the kernel. When a user logs in, the system launches the shell. It processes and executes commands typed in a terminal or stored in scripts, enabling communication between the user and the kernel. During the initial boot process, the operating system's core component, known as the kernel, is loaded into the computer's main memory, RAM. Once active, the kernel manages and allocates essential hardware resources such as CPU processing power, memory allocation, and input-output operations, ensuring efficient operation of the entire system. The shell serves as the primary user interface within the operating system, offering both command line and graphical interfaces depending on the configuration. It provides APIs that facilitate seamless communication and interaction between the end users and the underlying kernel. Additionally, the shell functions as a command interpreter, translating user commands into executable instructions for the kernel. In some environments, it also supports compilation tasks by integrating with development tools, enabling software creation and debugging directly from the interface. A wide range of utilities is included in the operating system, encompassing various management tools and specialized applications designed to enhance functionality and streamline administrative tasks. Here are some commonly used shells. The Bourne shell was created by Steve Bourne at AT&T and was named after him. It serves as the default shell for Unix systems and works on all Unix and Linux platforms. While highly effective for shell scripting, it falls short in interactive user experience compared to other shells. Bash extends the Bourne shell with improved features like command completion, editing, and history. It combines the strengths from both the C shell and the Corn shell, offering robust editing tools and an easy-to-use interface. Most Linux systems now use Bash as their standard shell. C shell, created by Bill Joy at UC Berkeley, is another popular shell after SH. Its syntax resembles the C programming language, which is why it's called the C shell. Tank C shell improves on C shell by adding command completion and stronger syntax features. The Corn shell combines the features of the C shell and the Bourne shell while maintaining full compatibility with the Bourne shell. Linux offers PDK shell, an enhanced version of the Corn shell that allows manual control. You can suspend, run in the background, resume or terminate commands directly from the command line. Corn shell is commonly used in Unix systems like HP Unix. Unix and Linux programs or commands perform single tasks. You can solve complex issues by chaining multiple commands together. A basic shell script is an executable file containing a sequence of commands that other scripts can reuse. You can open a new file in any text editor to create a shell script. Advanced editors like Vim and Emacs offer features such as the syntax highlighting, checking, and auto-completion upon recognizing files with the .sh extension. Shell scripts require an interpreter to execute and produce results. The interpreter is typically defined on the first line of the script, while it may run in a default interpreter if unspecified. Specifying one ensures standardization and enhances security. Here is an example syntax. Always define the interpreter explicitly for clarity and reliability. There are two modes to execute the shell scripts. In Linux, everything is a file. A script, command, or program is a file. A file is an object and has permission attributes. You may encounter permission problems when executing the script file. In this case, you only need to grant the execute permission. Sometimes, the execution of some scripts takes a long time and the CLI is occupied. In this case, you can run the scripts in the background. In this method, the script process is terminated after you exit the shell. To ensure that the script runs continuously, you can use the following method. You can run the jobs command to view the processes running in the background. In a Linux operating system, every running process inherently contains a text stream as an essential component. During the initialization phase of any Linux process, 3 fundamental text stream communication channels are automatically activated. Standard input, sometimes denoted as stdin, handles data entry into the program. Standard output, sometimes denoted as stdout, is responsible for displaying normal program results. Standard error, sometimes denoted as standard ERR, is dedicated to conveying error messages or diagnostic information. These 3 critical interfaces serve distinct functional purposes. Standard input is typically used for receiving data from a user or another program. Standard output is where the program sends its normal results for information. And standard error is specifically designed for reporting errors, warnings, or diagnostic messages. Sometimes you need to save a program's output. You can do this by redirecting its output to a file. When redirecting output, you have 2 main options. You can direct the output to a file, which will override any existing content in that file. Alternatively, you can append the output to the end of a file, preserving its original contents while adding the new information. Similar to output redirection, input redirection redirects the standard input of a program. Use the file on the right as the standard input, and then pass the command to the left. Output redirection requires files, while inline input redirection can use instant input text as standard input, passing in the command on the left. The character marker on the right indicates the start and end of the standard input. It is not included in the standard input. You sometimes need to connect the output of one command directly to the input of another, while you could try to achieve this with redirection. It is quite complex and unwieldy. A more elegant solution exists: pipes. Think of a pipe much like a real water pipe. It links the output of one command to the input of a second command, or even connects multiple commands together in a continuous sequence. This creates a seamless flow of data between different processes. The format for using pipes is straightforward. You simply place the pipe symbol between the commands you want to connect, like this: Command 1, vertical bar, Command 2, vertical bar, Command 3. This tells the system to take the standard output of Command 1 and feed it directly into the standard input of Command 2, and so on. At a fundamental level, pipes are a powerful form of inter-process communication. They allow separate programs to communicate and share data efficiently without needing temporary files or complex programming, making them an indispensable tool in the Linux command line. Just like any other programming language, the shell has its own set of reserved words and special characters. These aren't just arbitrary symbols. They hold specific meaning for the shell and instruct it to perform certain actions. Pay close attention to them when you are writing your scripts, as misunderstanding their purpose can lead to unexpected behavior or errors. Here are some of the most common important ones. Hash. This is the universal symbol for a comment. Anything following a hash mark on the line is ignored by the shell, allowing you to add notes and explanations to your code for clarity without affecting its execution. Single quotes. These are used for literal string references. When text is enclosed in single quotes, the shell treats every character inside literally, preventing any special characters within from being interpreted by the shell. Backslash. The backslash is an escape character, meaning it changes the interpretation of the character immediately following it. It essentially tells the shell to treat the next character literally, even if that character usually has a special meaning. Forward slash. This character serves as the path separator in Linux and Unix-like systems. It's used to delineate directories in the file path. Exclamation mark. In shell scripting, especially within conditional statements or loops, the exclamation mark typically represents logical NOT. It inverts the truth value of an expression. Just like virtually any programming language, the shell incorporates the essential element of variables. Variables serve as named containers for storing data, allowing programs to manipulate and recall information during execution. However, the way variables are handled in the shell presents a distinct contrast to many other languages. Unlike strongly typed programming languages such as C, Java, and C++, where you must explicitly declare a variable's data type, integer, string, or boolean, before using it. Variables in shell are notably classless or untyped. This means you don't declare whether a variable will hold a number or text. The shell treats all variable values as strings by default and attempts to interpret them as numbers when mathematical operations are performed. This flexibility can be convenient, but also requires careful handling to avoid unexpected type-related issues. Fundamentally, a variable can be thought of as a symbolic reference to the value of a specific memory area. Instead of directly manipulating memory addresses, you interact with an easily readable name. The variable name is simply the label attached to this memory area, providing a human-friendly way to access and modify the data stored within it. Assigning a value to a variable in the shell is very straightforward, following a simple and intuitive format. It's crucial to remember that there should be no spaces immediately around the equals sign when assigning the value to a variable in shell scripting. This simplicity in assignment makes shell scripting quick and efficient for many tasks. There are two fundamental categories of variables you will encounter in the Linux shell: environment variables and user-defined variables. Beyond these categories, variables are further classified by their scope, specifically whether they are global or local. Global variables are far-reaching. Their influence extends across your entire shell session and to any subshells you might launch within it. In contrast, local variables have a more confined reach. They are active only within the specific process where they are defined and any sub-processes that originate from it. To inspect the global variables currently active in your Linux shell, type print env. This will display a list of all variables that are accessible across your entire shell session and any subshells you create. If you want a more comprehensive look, including local variables, global variables, and even those user-defined ones for a specific process, type set. When you are working in a Linux shell, you will often need to modify variables. While you can change them temporarily in your current session, sometimes you will want those changes to stick around. To ensure your variable modifications are permanent, meaning they will be there every time you open a new shell session, you will need to add an export statement to one of your shell's configuration files. The two most common files for this are .bash_profile and .bashrc. When you are working with variables in the Linux shell, there are a few important naming rules you need to follow. Sticking to these conventions ensures your scripts run smoothly and are easy to understand. First off, a shell variable name can be composed of three types of characters: digits, letters, and underscores. No spaces, no hyphens, no special characters like an exclamation mark. Second, crucially, a variable name must start with either a letter or an underscore. You absolutely cannot begin a variable name with a digit. Finally, you need to be mindful of keywords that are reserved by the shell itself. These are words that have a special meaning to the shell and are used for its internal commands and syntax. You cannot use these keywords as variable names. For instance, you couldn't name a variable if, while, for, export, or echo, as these are built-in shell commands for control flow statements. Using them would confuse the shell and lead to unexpected behavior or errors. To define a variable, you can use any of the following three formats. If you are concatenating a variable with other characters and there's any ambiguity about where the variable name ends, always use curly braces around the variable to ensure correct expansion. It's a small detail that makes a huge difference in robust shell scripting. In the following example, if braces are not used, Bash interprets $first_$last as the variable $first_ followed by the variable $last instead of the variables $first and $last separated by an underscore. In this case, you must use braces to enclose the variable to make variable expansion work correctly. Here's an example to define the assign values. Declare a variable named name and assign it a string value representing a name, such as openEuler. Declare another variable named time and assign it a numeric or string value indicating a time, for example, 2025-07-22. Then you can read the input and output the variables. While the shell isn't a full-blown calculator, it does offer arithmetic extensions that let you handle simple integer calculations with ease. The syntax for using these arithmetic extensions is straightforward. You simply enclose your desired expression within square brackets, preceded by a $sign. This format ensures clarity and ease of use when performing calculations. Here are the arithmetic operation priorities listed in descending order. Let's break down the essential structure of the if-then-else statement in shell scripting. This is a fundamental control flow mechanism that allows your scripts to make decisions and execute different commands based on whether certain conditions are met. The if or elif keyword initiates the conditional block. This must be immediately followed by the condition itself. After specifying the condition, use the then keyword to indicate the start of the action block. Ensure there's either a space or a new line character separating the condition from then. Following the then keyword, you can list one or more commands. These commands should be separated by either spaces or inline execution or new line characters for better readability when multiple actions are involved. To mark the end of the entire if-then structure, always conclude with the if keyword. This signals that no further conditions or commands belong to this specific block. Typically, conditions within an if or else-if statement are enclosed inside square brackets to ensure proper evaluation. This structured approach ensures clarity and correctness when implementing conditional logic in scripts. The Bash shell executes the command following if first. If the exit status code is 0, the Bash shell continues to execute the commands in then. Otherwise, the Bash shell executes the next command in the script. When multiple conditions need to be evaluated, using complex if-then-else statements can become cumbersome. For scenarios where the same variable's value is repeatedly checked, the else-if statement is often employed. However, in such cases, the case statement proves to be a more efficient and suitable alternative. The case command is used to compare a specified variable against various predefined patterns or modes. When the variable's value aligns with one of these modes, the corresponding set of commands within that mode is executed by the shell. To streamline your code and handle multiple matching conditions efficiently, you can employ the vertical bar operator. This allows you to list several modes on a single line, separated by this symbol, enabling the execution of the same block of commands for any of those matched modes. Within the case structure, the asterisk serves as a catch-all wildcard. It is designed to capture and process any input values that fail to align with the explicitly defined patterns, ensuring comprehensive handling of unexpected or unmatched cases. Each mode's command sequence concludes with double semicolons. This syntax signals the termination point for the commands associated with that specific mode, clearly delineating where its operations end before transitioning to evaluate subsequent modes. The entire case statement is finalized using the keyword ESAC, which effectively marks the conclusion of the conditional evaluation block. This ensures proper enclosure and organization of the decision-making logic implemented through the case construct. Shell scripts often contain some repeated tasks, which are equivalent to cyclically executing a group of commands until a specific condition is met. There are 3 common loop statements: for, while, and until. There are 2 types of loop control characters: break and continue. They are used to control the direction of the loop process. Use a for loop when it's necessary to execute a series of instructions repeatedly until a particular criterion is satisfied. This technique is particularly useful for handling tasks such as iterating through every file within the directory, managing each user account present on the computer system, or sequentially reading and processing each line contained within the text document. The syntax, which is represented in both the shell scripting and C programming language formats, is outlined as follows. The while loop is a pre-test loop. It is used to perform some repetitive tasks that may be executed one or more times based on some conditions. To avoid infinite loops, ensure that the loop body contains the exit condition. The while command combines elements of an if-then statement and a for loop. It evaluates the result of a text command. If the result is 0, it runs the commands inside the loop. If not, the loop ends. The until command works in the opposite way to the while command. The bash shell executes the commands in the loop only when the until text command returns a non-zero value. Once the text command returns 0, the loop ends. Administrators who write, use, or maintain shell scripts inevitably encounter script errors. Errors are usually caused by input errors, syntax errors, or incorrect script logic. When writing scripts, using a text editor in conjunction with the bash syntax highlighter helps make errors more obvious. The most direct way to find and correct errors in a script is to debug. Another simple way to avoid introducing errors into a script is to follow a good style during script creation. To activate the debugging mode on a script, add the X option to the command interpreter in the first line of the script. You can modify the script file as follows. The debugging mode of bash prints the commands executed by the script before the script is executed. The results of all shell extensions that have been executed are displayed in the print output. The state of all variable data is printed in real time for tracing. Each command returns an exit state, or a return status code, or exit status code. The exit code can be used for script debugging. The following examples illustrate the execution and exit state retrieval of several common commands. When the script runs, it continues until all its code completes. However, if an error happens or you want to stop it early, you can use the exit command. This stops the script right away, skipping any remaining code. To write a shell script, the following are some specific practices to be followed. Divide a long command into multiple lines of smaller code blocks. The shorter the code segments, the easier for readers to understand them. Arrange the beginning and end of multiple statements to see where the control structures start and end, and whether they are closed correctly. Indenting lines containing multiple lines of statements can express the hierarchical structure of the code logic and the flow of control structures. Use line spacing to separate command blocks to clarify the start and end of code segments. Use the same format throughout the script. Add comments and spaces to improve script readability. These simple methods greatly facilitate users in finding errors during compilation and improve the readability of scripts for future readers. The following code lacks clarity and is difficult to read. The revised version is as follows. Well, this concludes today's course. We hope you found it enlightening. Feel free to join in our community discussions. And remember to follow us on our socials. See you in the next course. Thank you for watching.